So our next topic is not really a topic that's in the book explicitly, at least as far as one of the sections in the book, so we'll cover it here. We're going to talk about proving causation. So a few things that you should get out of this lecture would be some of the different ways involved in proving a cause and effect relationship. So there's 5 of them that we'll discuss here. You should know what a longitudinal study is. Sometimes these are called cohort studies as well. Make sure you know what a longitudinal study is. In demonstrating a proof of causation, we're going to use as a case study climate change. So in addition to knowing what a confounding variable is, I'm going to ask that you know what the difference is between climate and weather. So these are the things you should be getting out of our discussion here today. So I'll first go over what those different 5 ways are in proving causation, and then apply them to a kind of a case study of climate variation. Your grade in this course does not depend on what you think or feel about climate change. It depends on, do you know the statistical aspect of this? So let's go. The first thing that's important in discerning whether or not there's a cause and effect relationship is the temporal relationship. If there's a cause and effect relationship, generally the cause comes before the effect. The chicken and the egg kind of discussion. So having the correct temporal relationship is one of the things we're going to look at. Another thing you should see when you're looking at whether or not there's a cause and effect relationship is a replication of studies. You should see study after study coming to the same kind of conclusion. There shouldn't be a lot of disagreements amongst various studies. So, for example, smoking. Smoking has been pretty well established to cause a whole host of problems, including lung cancer and heart disease. The same thing is true with our case study today, climate change. Now, when I was growing up, back in 19 there was a scare that, we're headed towards an ice age. I remember having nightmares of a huge glacier towering over the Renaissance Center and wondering, gosh, what are we going to do about it? We're all going to freeze. Well, what happened back then was that there was a paper that concluded that ice age, or global cooling might be a possibility. But even back then, the preponderance of papers and studies were predicting a global warming. But it just happened that this one paper caught a lot of attention and a lot of publicity, so perhaps myself and a lot of other people grew up for a while thinking that the Earth was cooling. There should be, in a lot of cases, there's going to be a dose response. That is, the more of the cause you get, the more of the effect you get. So this one demonstrated here might be more of something related to a medicine that you could take, etc., and then the responses you can get from that. But a lot of times there should be a dose and response kind of effect. You saw that, or you could have seen that with studies in the fluoridation of water. When they started introducing fluoride to water, the proportion of cavities you started seeing in kids of a certain age started decreasing in a nice trend related to how much exposure they had to fluoridated water. Same thing with the chance of getting lung cancer and how much cigarettes you smoke. There's a nice correlation there. So that correlation can be turned into a causation. Now, one that we're going to spend a little bit of time on is a longitudinal study. Longitudinal studies are studies that look at a group of people for a long period of time. and they follow them. That group is sometimes called a cohort. Now, one of the nice benefits of a longitudinal study is that you can help rule out what are called confounding variables. So let's understand some stuff about a confounding variable, starting with a definition of a confounding variable. A confounding variable is a variable whose presence changes the relationship between the independent and dependent variables. So it kind of mixes the picture up a little bit. If you knew this, then you might change your opinion about something. If you're doing, for example, a study on heart disease and obesity, okay, there is a link there. But in studying that, there's other variables that you want to consider. Age. Age is an important factor. Whether or not you smoke is going to be an important factor. How much you exercise, what's your diet, what's your cholesterol level, what's your heredity. These are all things that come into play when you're trying to understand the relationship between, say, obesity and heart disease, or really just about anything in heart disease. A lot of what we know about heart disease came from a very famous study that started in 1948 called the Framingham Heart Study. And they followed people for years, decades. In fact, I think they're on their third generation of following people. And it's told us a tremendous amount of information regarding the predictors of heart disease. All right, so what are some of the things that you have to be a confounding variable? Confounding factor must be associated with both the risk factor and the outcome. So with the independent variable and the dependent variable. But we don't want it to be part of the causal chain. We just want it to be associated with both of those. So the confounding factor must be associated with both the risk factor of interest and the outcome. So the x variable and the y variable. A nice thing about the confounding, or about a longitudinal study, is that even though you might not be measuring specific confounding variables, if you assign groups of people to kind of a treatment group and a control group, hopefully you'll get a balance in these risk factors. Hopefully you're not going to get all the people who don't exercise and eat a high cholesterol diet in one group, and people who are young and have good genetics in another group. Hopefully a lot of these things even out. And that's one of the advantages that you can see in a longitudinal study. And last but not least, the confounding variable can't be a step along the chain of your cause and effect. It can't be part of the causal pathway. It has to be independent of that pathway. Now, longitudinal studies are great in terms of deciding, what factors are relevant in making predictions for instance, heart disease or lung cancer, global warming, etc. But let's take a look at some of the advantages and disadvantages of a longitudinal study. So longitudinal study, like I said, is called a cohort study. Some of the disadvantages are that it's costly. They're really expensive. You have to follow a group of people for a long period of time, years, decades. And in that time, not only does it take a lot of time to follow these people, but then there's a loss to follow-up. People drop out for different reasons. They lose their motivation. They move. They pass on. So longitudinal studies are really, really difficult. But they are nice and flexible. So you're going to follow a group for an extended period of time. Like I said, it's flexible. You can change things up as you're going through your study. And a good example of one is sildenafil citrate was a medicine that was being tested in a study, and it was originally supposed to help lower blood pressure. And as they're going through the study, they decided, you know what, it just isn't working. And they wanted to end the study early. So all these men who were getting this drug, they were asked for this, just send it back. And the guy said, no. And they wanted to keep their medicine, this experimental drug. And Pfizer became a little bit curious. Well, gee, why do you want to keep it? Well, I'll let you kind of infer the reason they wanted to keep it, because eventually sildenafil citrate did come to the market, and you'll know it as Viagra. So it was kind of an accidental discovery on the part of Pfizer as to why they didn't want to return their medicine. As I said, one of the good things about a longitudinal or cohort study is that it's good for helping establish a cause and effect relationship, because you try and distribute all these confounding variables equally amongst different groups, so that you're not going to have a large proportion of, one group having some kind of confounding variable, whereas the other one didn't. Sometimes you don't know what the confounding variables are, so you do a large study and you hope that things average out so that you don't get a confounding of your result. At some point in trying to establish a causal relationship, you need to be able to explain it. Well, why is this happening? Why does smoking cause cancer? Oh, well, because some of the 4,000 chemicals in cigarettes bind with radioactive radon in the air, and when you suck it deep into your lungs, because they put menthol in your cigarette, when you suck it deep into your lungs, that radioactive radon changes your DNA, it mutates it, and that mutation causes cancer. Okay, that's a nice causal effect. You're explaining what you see. One of the challenges of dealing with a less expensive study, a so-called cross-sectional study, is that when you're just looking at cross-sectional data, just looking at people at one specific time, the most you can draw is an association. We'll work on that stuff in Chapter 11. But you should be able to explain things, process or pathway in which the outcome is brought to being. Now today we're going to work on establishing a cause and effect relationship. We're going to look at this type of statistical analysis with respect to climate change. And one of the things that I ask you to know for climate change is the difference between climate and weather. Anyone describe to me what's the difference between climate and weather? Yeah. Weather is what's happening outside your window right now. Right where we're at. Weather is happening today. Climate is averages, long-term changes, variations in weather patterns. The way I like to say it is weather changes with the day, climate changes with the latitude. So climate is going to be some long-term trends. It's not going to be based on whether or not it's rainy or sunny in one particular day, or if it's really cold or really hot. What happens in any particular day doesn't matter. That's what the weather is talking about. Climate is long-term trends. So let's apply climate, or let's apply some of these 5 criteria to the argument for or against man-made climate change. So the first thing there is a temporal relationship. What's coming first? Is it carbon dioxide causes an increase in temperature, or is it the other way around? When you look at some data, it's not always clear. What is clear is that there's an association. They seem to go up together. but sometimes there seems to be like a little bit of a lag. Sometimes one seems to be ahead of another. That's okay. You can see a lag or other things in climate data. In smoking data, here's smoking rates versus lung cancer rates. Notice that these look similar in shape, but one lags the other one by about 20 years. Well, yeah, lung cancer doesn't happen overnight, so it's going to take a while before that develops. So there's a little bit of a lag. So that's consistent with our thinking. But as far as what's going on with CO2, sometimes the level of CO2 can increase before the temperature, and sometimes the temperature responds to the increase in CO2. So what's happening there? You don't get this nice clear-cut picture like we do with smoking. And the example that I would like to put forward is like a can of pop. If you open a can of pop when it's cold, when it's really cold, you're going to get some bubbles that come out of it, but not as many as if you did that when it's really, really warm. When you open it up when it's really, really warm, it's going to be much more anxious to get rid of its carbon dioxide. The same thing happens with the oceans. The oceans are going to release more carbon dioxide when they're warmer as opposed to it's cold. And what happens is you get kind of a feedback loop. You get a little bit of warming, maybe the Earth's position changes with respect to the sun, and you get more carbon dioxide in the air. More carbon dioxide means you're putting a blanket around the Earth, and that traps some more of our warmth. So, okay, now your CO2 level is increased, now you're getting more warming, etc. And you get this continuous feedback loop that changes your climate. Replication of studies. So one thing you should see if something does have a true cause and effect relationship is that different studies come to the same conclusion again and again and again. So, in looking for this, I found this. There's a website right here if you want to go check it out, petitionprojectorg. And this website says that they've got 31,487 Americans with university degrees, including over 9,000 with PhDs, who made a clear, strong statement that they just don't think global warming is real. Okay. Doesn't sound like a consensus to me, does it? Now, in looking at this further, I found out that this website is based out of the Oregon Institute of Science and Medicine. Who? Has anyone ever heard of that? I don't even think it's a real college or university. They had some faculty there, but when I clicked around trying to find, gee, what courses do you offer? What's your mascot? Who's your football team? You know, there's like nothing. It's in the middle of nowhere in Oregon. So, all right. So a more credible paper is one from Toll, and he says that, gee, there really isn't a consensus on this. But the way he determined whether or not there was a consensus was he just looked at the abstracts. And if the abstract didn't say, gee, we think global warming is man-made, then he said, oh, okay, well, then we're just going to throw this out. And if you apply this to other areas of science, such as plate tectonics, which we've agreed about for 40 years, then using his analysis, you would reject that there's a consensus on plate tectonics, which there is. Now, let me ask you a question. What percentage of peer-reviewed papers do you think you should see out there before you would feel comfortable that there's a consensus? I mean, do you want 60%, 70%, 80%, 90%? At what level do you think that the number of people who agree, the percentage of people who agree, form a consensus? Just throw out a number. I want to hear from you. 75, 80? Okay. Other opinions? Anyone else? We agree with Chris? Jacob? 50? Okay. All right. So, just so you know, there's a lot of people who don't, maybe not a whole lot, but there's a lot of people who don't think that smoking causes lung cancer. About 9%. It actually went down from 1999, which I find amazing, but okay, that's fine. Free country. As far as a consensus on global warming, the study that I found that I thought was really well done showed that 97.2% of people who research global warming think that it's a man-made phenomenon. Wow, that's pretty high agreement. I mean, that's even better than people agree on in smoking. So, wow. Now, dose response. The more you smoke, the higher your chance of getting lung cancer. How about in terms of global warming? Global warming, the big culprit is carbon dioxide. If you take a look at the historical record going back 400,000 years, take a look at the levels of CO2 and temperature. CO2 is in blue, red shows the temperature. They look like they're in pretty large lockstep, right? So high concentrations of CO2, high temperatures. Low concentrations of CO2, low temperatures. Okay, wow. Looks pretty good, pretty convincing in terms of a dose response. And besides, we know the physics behind it. Now, one of the things that longitudinal studies can do is rule out confounding variables. Some of the possible confounding variables for understanding the relationship in global warming: changes in the amount of sunlight received, changes in the Earth's orbit called the Longitudinal cycles, the amount of CO2 from volcanoes, and hey, the climate changed naturally in the past, so it's doing so now. So let's look at each of these variables. And there's more too, but I want to keep this list kind of short. If we were getting changes in the amount of sunlight received, then if that was the source of global warming, what you would expect is the upper atmosphere and the lower atmosphere, that is the surface, both to warm. If instead we're seeing an effect from carbon dioxide generated in the lower atmosphere, then what you would see is what we are getting, and that is an increase in surface temperature, but a decrease in the temperature of the upper atmosphere. And we can and do measure that, and that's what we're seeing. So we can rule out that confounding variable. Changes in the Earth's orbit can affect the amount of sunlight we receive. So maybe that's a possible explanation for why we're seeing a spike in global temperatures. But if this were the case, then based on the Longitudinal cycles, then we should actually see a little cooling of the Earth right now, based on different things about the position of our orbit. I'm not going to try and go through the Longitudinal cycles with you. Natural variation. Okay, so you might look at the historical record. And by the way, does anyone know how you get the historical record? How do we know what things were like hundreds of thousands of years ago? CNN wasn't there to measure it. The Weather Channel wasn't around. Yeah, ice cores. So you drill back, and you can count the layers, and through chemical analysis you can figure out a lot of things. The science of ice cores actually started with a guy by the name of Claire Patterson, who was investigating the age of the Earth, and he needed to determine historical lead levels. And he figured out, you know what, there's lead everywhere, because they started putting it in gasoline. And he reasoned that, you know what, I can look at historical levels by drilling down into ice cores. So All right, so looking at things in the past, yeah, we have some variation, some natural variation. But what we're seeing right now is a much too dramatic increase to say that, oh, gee, it's just natural variation. In fact, this doesn't tell the story here. What I have circled in yellow there is a spike at the end. That spike only goes up to 383. If you're to look outside today, then that level should be about 410. So basically it would go over the top of our chart here. Let's practice some type 1 and type 2 errors again. So if you're doing a hypothesis test, you can start out and say, you know what, we're going to assume that climate change is not man-made and test it against climate change is a man-made phenomenon. So that would make a type 1 error a false positive, saying, you know what, we think climate change is real when in fact it's not a man-made phenomenon. So what are some of the consequences there? Well, you can spend more on your energy bill because you're going to have to find different ways to conserve, maybe use cleaner fuels, less dependence on coal, etc. There could be a loss of jobs in the fossil fuels sector. Could be inconvenient, and prices might go up for petroleum-based products. All right, so those are things to be concerned about in terms of a type 1 error. What's a type 2 error? Well, type 2 error in this case would be failing to reject the hypothesis that global warming is not a man-made phenomenon when it really is. All right, well, so we don't act on things. What are some of the consequences of not doing anything and global warming is real? You're going to see more severe weather, warmer winters. Now, warmer winters sounds great. I mean, I've enjoyed having warmer winters around here, but there's a problem. You're going to have more and more diseases brought north. And I don't know about you, but was it last summer? What was the big disease down in Florida? The one that the Zika virus. Okay, that kind of thing can spread to more northern latitudes if you don't have a cold winter to kill off all these bugs that carry this stuff. So that's kind of a problem. Reduced areas for agriculture. All right, kind of a bummer there. It might be made up, if you have areas that are farther north now that all of a sudden are suitable for agriculture. Rising sea levels. This could be a problem for coastal areas. Certainly there's a lot of islands in the Pacific that are worried about this kind of stuff. A lot of problems for animals in terms of change of migratory patterns, and we're seeing this now, that they're leaving and coming at different times, and the extinction of species. So the big thing that we don't know about is what's going to happen to the big driver of the Earth's climate, which is thermohaline circulation. A big word, but it really means how the oceans circulate currents. This is the reason that Europe is much more temperate and doesn't have the climate of Alaska, because it gets a lot of warming waters that help keep it a little bit more moderate. So, and some health threats. So, all right. Any questions or thoughts on proving causation here? All right. Make sure you know what the 5 different things are that prove causation. Know the difference between climate and weather. Know what a longitudinal study is. And know what confounding variables are. Those are the things that you're responsible for from this presentation.